Problem 4.34. In this problem, there is a fluid with a velocity along the x-axis, as shown below, that changes from 6 meters per second from point A to 18 meters per second in point B. It is also known that the velocity is linear as a function of the distance along the streamline. We need to determine the accelerations at point A, point B, and point C. Okay, so let's start with the information that is given. They gave us a velocity at point A to be 6 meters per second, a velocity of point B, which is 18 meters per second. They also told us that the distance between point A and point C is equal to 0.05 meters, and the distance between point A and point B is equal to 0.1 meters. Okay, they also told us that the velocity is along the x-axis and is linear, so the velocity is going to be in a form c1x plus c2 to make it linear. Okay, and what we need to find is we need to find the acceleration of x at points A, B, and C. Okay, so for the assumptions for this problem, we are going to assume that is a steady state, there is no change with time, and also that it is going to be one-dimensional, only on the x-axis. So the first thing that we need to do is determine what are the constants, c1 and c2, to be able to determine the velocity profile. So for that, we evaluate the velocity. So we know that the velocity at position 0 is equal to 6 meters per second. And we simply substitute x to be 0 into the equation. So it's c1 0 plus c2. By inspection, notice that if this is 0, c2 is equal to 6 meters per second. And then we do the second equation, which is velocity of u at point B, which is 0.1 meters, is equal to 18 meters per second. And we do it again. c1, we put the value of the distance, which is 0.1 meter, plus c2, and that is equal to 18. We solve for c1, and we find that the value of c1 is equal to 120, and the units are going to be 1 per second. Therefore, the velocity as a function of x is simply 120 x plus 6. And we're just not going to carry out the units. We already have them for c1 and c2 over here. Okay, so now we're going to evaluate the acceleration. Acceleration is simply going to be du dt, and that is simply partial derivative of u respect to t, u du dx, v du dy, w du dz. Since it's one-dimensional, these two terms go away, and it's a steady state, so this term goes away. Therefore, your acceleration, du dt, is simply going to be the velocity, which we have it to be simply 120 x plus 6, and the derivative of u with respect to x. So if this is the velocity, we take the u dx to be simply 120. So the 120 is the derivative of this. So we substitute it back over here. And then this gives us that the acceleration is equal to 14,400 x plus 720. So now we have to do is substitute each one of the values for x into the acceleration to get the value at each one of the points. So at x a is equal x is equal to 0. We substitute the acceleration to be 0 in this place, and it gives us 720 meters per second square. If we evaluate it at point B, we have that the position is equal to 0.1 meters. Once again, we substitute it into this point, so I'm just going to call this A and this B. We substitute at x to be 0.1. We substitute it, and it gives us 2,160 meters per second square. And then the last one we have is at position C, so it's xc, which is at x equal 0.05. We substitute it in here, and we find the acceleration at point C. Once we substitute it, it's going to give us 1440 meter per second square. And as we can see, the value of the acceleration increases as a function of the velocity, as a function of the position.